Any questions from last time, the atomic theory periodic table? Did we get to everything? Let's see.
Something we were still working on.
Did we talk about ions last time? Cations and anions?
A little bit.
Okay. Well, that's all there is to it. It's just cations and anions. Did we talk about valence electrons last time? Okay, so yeah, we finished. But now let's actually use that stuff. Great, we just memorized all that stuff on the periodic table. Now let's use it, and hopefully that'll help it to sink in. Any other questions before we get started? Yeah, Marcella.
Could you quickly go over again the multiple proportions? Just because I know you mentioned how you have to divide by the smallest number.
You don't have to actually.
You don't have to?
You just have to make sure in one of the atoms you have the same amount of mass. And then you compare the ratios of the masses of the other one once you keep it the same ratio. Right? But here's the takeaway. So the law of multiple proportions will hold if the two compounds are made of the same elements. So if you have one that has one different element, it's not going to hold. And so on the exam, it might ask you something like, which one will not follow the law of multiple proportions? Do you have to do any math? You really don't. Now, later on, we're going to learn about empirical formulas, and we're going to do something similar to that with empirical formulas, and you have to be able to do that. But it is a little bit different, so I don't push this too hard. I mean, if you want, I will still go over the calculation. Would you like me to?
Well, there was the one that's like sulfur and oxygen on the worksheet.
Uh-huh.
And I was trying to look it up on the key, and it's a completely different problem.
Oh, is it?
Yeah.
I must have decided to change one because I wanted to pick one that doesn't look like it's the same ratio, because it's always 2 to 1, and you say, I don't even have to do that math if just look at it, it's a 2 to 1 ratio. And so I tried to pick one that maybe it's not easily noticeable. But if they have the same two elements, it's a law. It will follow that. But if it has not the same two elements, it will not. Does that make sense? Any other questions? Okay. All right. Today we are going to learn about compounds, how to name the different types of compounds, properties of the different types of compounds. So the two types of compounds are ionic and covalent. So we got to know the difference between these two. And we name them differently. We write the chemical formulas a little bit differently. And so that's what we're going to learn today. Okay, so first of all, we talked about valence electrons. Everybody get your periodic table out, and if you need one, I can give you another one. So let me know. Okay? If you need a periodic table, come grab one, because I'm not going to bring it up to you.
Mine's so nice.
Yep, you're okay. Anybody else? And if you want an extra one, they're free for you.
Thank you.
Okay. All right, so looking at your periodic table, so this is just a little review. We're going to need this for today. How many valence electrons does sulfur have? Make sure you can do this. 16? 6, because it's in group 16. You with me? What about nitrogen? 5, because it's in group 15. Now, okay, here's a better way. The main group elements. Do you remember the main group elements? The first 2 columns and the last 6 columns? So the first 2 columns is group 1A and group 2A. The last 6 columns are group 3A, 4A, 5A, 6A, 8A, 7A, and 8A. Then it is the group number. You with me? But on this periodic table, you're not given group 1A, 2A, and so on. You're given just the group number. So I've just shown you how to predict how many valence electrons are in the main group elements. Are we okay with that? Okay. All right, so who can tell me what a valence electron is? Anybody? Yeah, you know.
Like on the outermost energy layer.
Yep. Electrons on the outside. And these, why do we have a special name for these?
They're reactive.
Yeah, they're the only ones that change in a chemical reaction. We don't worry about the inner electrons. It's just the ones on the outside. Okay? So now that we're talking about different compounds, well, how do we get these compounds? Through chemical reactions, right? And so we change the valence electrons in order to get them. So before we move on to bonding, let's talk about the octet rule. And the octet rule states an atom tends to lose, gain, or share electrons. And what electrons are they losing, gaining, or sharing? Valence electrons. In order to achieve, is I before E there? I know it's not a C, but is that good? All right. To achieve a noble gas. You guys remember where the noble gases are? Yeah. Noble gas configuration. And when I mean configuration, I mean electron configuration. And we're not going to really learn electron configurations until next unit, chapter 3, or section 3. Yeah.
By that, do you just mean to complete or lose its valence electrons to be stable?
That's right. So do you remember? Did I show you the Bohr model of the different atoms, and all of the noble gases all have what? A complete shell. Did we talk about this last time? Okay, good. Okay, so they got a complete shell. They're just perfect. They don't want to change. That's why we call them inert gases. And everything else, well, they do want to change so they can be like those noble gases. They won't become a noble gas, but the way that their electrons are will be like a noble gas. Good? So, for example, if we have magnesium, magnesium has how many valence electrons? 2. So I'm just going to draw them as 2 dots, right? That has more electrons on the inside, but I'm just drawing the outside shell, the valence shell, okay? Now, it wants to have how many? 8. Now, most of the time it is 8. Some of them, it's 2. Which noble gas has 2 valence electrons? Helium, right? But the nearest noble gas to magnesium is neon. And neon has 10 electrons total. Magnesium has 12 total. So it has 2 options. It can lose 2 electrons and be like neon, or it can gain 6 and be like argon. What is easier? Lose 2. You with me? Okay. So we're going to lose these 2. Now, originally magnesium metal, I just burned some last time. Or it didn't burn it, but I caught it on fire, right? Something like that. Okay. And, well, did it shock me when I touched it? No, it was neutral, right? All atoms are neutral to begin with. So it's neutral. And if we lose 2 electrons, what does lose? Add or subtract? Subtract, okay. And we lose 2 electrons. If we lose 1 electron, how much charge did we lose? -1. So if we lose 2, it's -2. What is 0 minus a -2? +2. You with me? And so the magnesiums, we talked about cations and anions last time, right? And all metals will become a cation. Remember this? This is a metal. It will lose 2 electrons and become Mg2+. And now its electron configuration is just like neon. You with me? It's balanced. It's perfect where it's at. Now it's happy. But it won't do it all by itself. It does it during a chemical reaction. And so the chemical reaction that we talk about when we gain or lose electrons is an ionic compound. Yeah.
So
Sorry, not the chemical reaction, the type of bond it makes. Yeah.
when we lose 2 electrons, it's +2. If we were to say gain 6, would it be -6? Mg -6.
It would be, but we will never do that.
Right. But
Yep. So let's just do another one. So let's say we have chlorine, for example. Chlorine has how many valence electrons? Has 7. So I'm just going to draw 7 dots around here. And so it's neutral to begin with. And what does it want to do? Gain 1, right? It wants to gain 1 to reach that octet just like, is it argon? Or is it neat? It's argon, right? Just like argon. So we start with neutral, so it's 0. And this time we're going to gain an electron. Gain means add, right? An electron is just 1 electron, so -1. That gives us a charge of -1. So we call this Cl-. Do we have to worry about 1? No. But if we did put a 1, and we could, it'd be 1-. Are we good? All right. And that's only going to happen during a chemical reaction. So what happens if this guy was going to bond with this guy? Can it? This is negative, and this is positive. What happens to negatives and positives? They attract. And that's what holds them together. It's an electrostatic force. This is the same force that holds our bodies together. Okay? Can we pull our finger off? If you pull hard enough. But it takes a lot of force, right? Okay? Don't try it, guys. Okay. Yeah.
So essentially it's just based on the loss or gain of electrons from a neutral state if it goes
Yep.
positive or negative.
Yep.
Okay.
And do we know how many it's going to lose or gain? We look at the periodic table, right? And we'll talk a little bit more about this in chapter 3 after the exam, next unit. Okay. So we'll see how far we get today. If we cover all this, then that's all there is going to be on the exam. Okay. If we don't, then I guess we'll finish it on Tuesday. Okay. But I think we should get pretty close anyway. Okay. Any questions on how an ion forms? So in the case of an ionic compound, it will lose or gain electrons. In the case of a covalent compound, it will share. We'll talk about those later. Okay? So let's talk about ionic compounds. Okay, another name that we give ionic compounds is salts. Just like the salt we put on our food, that is an ionic compound. But there's a lot of different types of salts. You guys ever have bath salts? Those are salts, right? Epsom salt. A lot of different types of salt. And all ionic compounds are salts. And what are salts or ionic compounds composed of? Could be, that's one example. Okay. What? Metals and nonmetals. So it's composed of a metal and a nonmetal. In general, that's what it is. Okay? To cover everything, an ionic compound is made of a cation and an anion. That is always true. So we're going to talk about some cations that are not metals, but all metals will become cations in a chemical reaction. Okay? So in general, for the most part, it's a metal and a nonmetal. Are we good? Okay. Another thing you need to know about ionic compounds they are always neutral in charge. So it's made of a cation and an anion. So the charges must neutralize. Otherwise, it won't happen. Okay? Has to be neutral. Covalent compounds, on the other hand, don't have to be this way. But ionic compounds must. Okay? So let's talk a little bit about the properties of ionic compounds. Any questions so far? We will get a little deeper, but so basically just basic information right now. How do you tell if a compound is ionic versus covalent in the end, right? So that's the purpose of knowing all these attributes of an ionic compound. So if it has a metal in it, it's going to be ionic, period, end of story, no exceptions. Okay? If it's covalent, it will not have a metal in it. You with me? You have a question there, Nick?
Did you just say they're always made up of cations and anions?
Yeah?
But isn't one of them always going to be a metal?
Nope, not always. Most cases, yes. We'll talk about those cases in a minute. Victor?
Covalent, is it correct to say covalent ions?
Covalent compound.
Covalent
Or
compounds.
bond.
They're always charged, right? They're positive or negative.
No. Covalent, they share electrons. And we'll talk about those in a little bit. Okay? So we will get there. Right now we're just talking about ionic compounds. And then we're going to talk about how to name and how to write chemical formulas for ionic compounds. And then we'll switch to covalent. Talk about the properties and how we know it's a covalent compound and its nomenclature. Sound good? Okay. All right, some properties. Some basic properties are ionic compounds. If they're salts, is it a solid, liquid, or gas? It's a solid, right? Now, it's not just a plain solid like metal is. It's a crystalline solid. Just like we look at salt, right? They're all crystals. You with me? So they're crystalline solids. Solids at room temperature. Okay. And they're not conductive by themselves, but lot of times we dissolve salts, right? Put salt in water or in something else that has water in it, okay? So when salts or when ionic compounds are dissolved, they are highly reactive. Sorry, no, I said the wrong word. They are highly conductive, okay? Highly conductive when dissolved in solution. Okay, if you're standing on a salt brick, it's non-conductive by itself. You with me? If you melt it or dissolve it, then it becomes highly conductive. It also has high melting points, very high melting points. You guys ever make caramel with sugar? Sugars are crystals, right? But sugar is a covalent compound. And you put it in the pan and you heat it up, what happens? It melts pretty quickly, right? Try that with salt. You'll never get it to melt. Not on the stove anyway. It melts like 800 degrees Fahrenheit, I think. Whew, that's pretty hot, right? So very, very high melting points. Any questions on the properties of ionic compounds? And these are just general properties. And do we ever have exceptions? Okay, yeah, we always do. Well, why do we have exceptions? We talk about this? Because we don't fully understand something. Really, who made these rules? People did, right? And so if something goes against it, that means it's not a law, right? It's not set in stone, okay? But anyway, we're going to just talk about the main things, okay? We'll probably will get to some exceptions. All right, so let's talk about how we write the chemical formula. So I'm going to start real simple. And you will have to know this for the exam. Writing chemical formulas. For ionic compounds. Or I might say predicting chemical formulas, right? So if we have a compound with sodium in it and chlorine in it. We got sodium and chlorine. Well, first thing we do is we count their valence electrons. Sodium has how many valence electrons? 1. And chlorine has how many? 7. And if these guys come together and just sit by each other, probably nothing's going to happen. So you have to give it a little bit of energy to make something change, right? So we just dealt with sodium last time, didn't we? You throw it in water and it reacts quickly, okay? And what happens is that sodium gives up its electron and becomes what? Na+. You with me? And chlorine does what? Where does he get the electron from? From the sodium. So it has to be close together for this to happen. And it becomes Cl-. One's positively charged, one's negatively charged. They're going to electronically attract. Laws of physics work for these guys just like everything else, okay? And, well, you have one positive and one negative. So how many of each of these do you have to have for it to be neutral, because all ionic compounds must be neutral. How many? One of each. This one's pretty straightforward. That's why I started with this one. Pretty easy. So what's the chemical formula going to be with a compound of sodium and chlorine in it? NaCl. And that's the stuff we eat every day in our food, right? Now, we kind of talked about this. I'm not sure if everybody was here, so I'm going to say it again. Sodium is very reactive. Chlorine is very reactive. Now, why? Why are these? So we said alkali metals are the most reactive metals on the periodic table. Why is that?
Because it's so close to the noble gases.
Yeah, they're just one away. All they need to get rid of one. They just need to get rid of one electron to be stable, or to be balanced, you might say, or efficient. And chlorine just needs to take one. It's also just one away. So the halogens are the most reactive nonmetals. And that's why. Are we good? Okay, so sodium, you don't want to eat it. You will die. Maybe, if you eat enough of it. If you eat enough water, you're going to die. Okay. But chlorine is a poisonous gas. Also bad for you. But together, we eat it every day and we're fine. So the compounds have different properties than the elements themselves. Just know that. Are we good? All right, let's do one that's maybe not as straightforward. Let's do magnesium and nitrogen. Okay. So we can draw all of this, but really we just need to know what its charge is, right? So can anybody tell me what the charge of the magnesium ion would be? 2 plus. We just did this one, right? Any questions on how we got 2 plus? Had 2 valence electrons, so we get rid of 2 electrons and it becomes 2 plus, or positive 2. You with me? Okay. And nitrogen, what type of ion would nitrogen become, by the way?
4 minus.
An anion or a cation?
Anion.
Anion, because it's a nonmetal, right? So it's going to be nitrogen with a what charge? 3 minus, because it has 5 valence electrons. It can either get rid of 5 or gain 3. What's it going to do? It gains 3. It finds the nearest noble gas and says, okay, that's what I want to be like. Are we good? Now, I can show you something that one of my students showed me in high school. And if you look at the periodic table, look at magnesium. How many electrons, total electrons, does it have compared to the nearest noble gas to magnesium? 2 more. 2 more, 2 plus. How many how many electrons, total electrons, does chlorine have compared to the nearest noble gas? Sorry, not chlorine. Nitrogen. 3 less. 3 less, 3 minus. Make sense? That's pretty cool, right? I mean, that's a quick trick to say, okay, that's how you can figure it out. But why didn't I teach you that way to begin with? Because I like to teach you how it is. You with me? Okay. So now, how many magnesium... Yeah, Victor.
Sorry, I'm not necessarily following how it gained 3. Magnesium had 2 valence electrons, right? And it gave
So forget about magnesium when we do nitrogen. Nitrogen has 5 valence electrons. You with me?
It wants 8. Okay, they didn't
Okay.
necessarily come from
Yeah.
magnesium.
So here's what happens. Nitrogen wants to gain 3, no matter who it bonds with. Okay? And nitrogen is not going to say, hey man, I'll take your electrons, but only if I get 3 of them. Right? You with me? Now, so how are these guys going to bond? This guy isn't even going to get rid of 3. Is that what you was wondering? Yeah. Milos?
Yeah, so what about the elements that are equidistant from either side, like carbon?
Yeah.
Just go either direction then?
will most likely share.
Okay, that'll be covalent.
Yep, most likely, okay? Well, great question. All right, so now let's talk about how many magnesium ions and how many nitrogen ions do we need in order to be what? Neutral. Good. They have to make a neutral compound because this is an ionic compound, right? So let's see. Here's the long way, and then I'll show you the quick way. Okay, here we go. The long way just tells you what's going on, right? And then I'll show you the quick way to do this. Okay? So if we have one magnesium, that's positive 2 charge, yeah? If we have one nitrogen ion, that is negative 3 charge. We add those together and we get negative 1. Are we happy yet? No. So we need more positive or more negative? More positive. Well, the only positive that's around is magnesium, so we have to add another magnesium. And what do we get? Positive 1. Now we need more negatives, don't we? So the only negatives is a nitrogen, so negative 3. We add that and we get negative 2. So now we have to add another magnesium before we get 0. You with me? And it does this almost instantaneously, guys. It doesn't, okay, come over here, wait, we need one more. Now you call your friends over. I'm not going to do that, okay? Almost instantaneously. So let's count how many magnesium ions we got. 1, 2, 3. And we always write the cations first. I'll give you some steps in just a minute. So we got 3 of those guys. And how many nitrogens do we have? 1, 2. And only 2 of those before it's neutral. So that is the chemical formula for a compound with magnesium and nitrogen in it. You with me? Okay, can you see a quick way? What do you do?
LCD, just find this common factor.
We could cross the charges. That's all we do. Now, there's something we got to make sure of. This is an algorithm, and you have to remember the algorithm, otherwise you're going to get it wrong, right? Or you can do it this way every single time. That way it always works, but it's kind of clunky, right? So we write the charge Mg2 plus N3 minus. We take the charges, just the number itself. We don't have to worry about the charge. And you cross it down, you get Mg3N2. Now we have to check one more thing. We have to make sure it is lowest. Oh, I didn't write that. Let's write that. Lowest whole number ratio. So what's the ratio of magnesium to nitrogen? 3 to 2. Can we simplify that fraction? No. That means it's done. Okay. So let's write some steps. Step 1. Write formula for cation first. So here's the formula for the magnesium cation, Mg2+. Do you all understand how to come up with that? And so far this is just for main group elements. We'll get to other ones, okay? Any questions on step 1? Step 2, write formula for anion second. So you put the cation first and then the anion. That's how we read it. From left to right, cation first, then ion. Positive before negative, right? And then step 3, we cross number of charge. We just cross them down. And then the last step, sometimes it's already done, like it was in the case of magnesium nitride, is we simplify to lowest whole number ratio. And this is how you do all ionic compounds. It doesn't matter what type. Okay? But maybe how to get this and how to get this might be a little trickier for some of them. Okay? I'm going to come up here, and we wrote the properties. I'm going to write one more thing for ionic compounds. I should have written this. Ionic compounds are written with lowest whole number ratio. Of atoms. Okay? Always. Covalent compounds, not so. Okay? Only for ionic compounds. So again, ionic compounds are written with the lowest whole number ratio of atoms. Always, always, always. So here's our steps again. So let's do one that's a little bit harder than those two. We ready? You have any questions so far? Okay. So let's say we have, I'm going to give you the charge because you can't find this one yet. Pb4 plus and S2 minus. So what do we do first? After we put these like this? Swap the numbers down. Pb2S4. Are we happy with that? No, it's a 2 to 4 ratio. Can we simplify that ratio?
Yes.
1 to 2. So that 2 becomes a 1, that 4 becomes a 2. PBS kids. Oh, I meant 2. Okay, sorry. We good? So make sure you simplify it if you choose to do it this way. This is the algorithm. You got to follow all steps if you want it to work. Yeah.
What is best practice in terms of writing subscript or superscript?
So I'm not sure what you mean.
So initially when you gave us the problem, it was 4 plus superscript, right, like exponent, and then the final answer after simplifying, you write it subscript below it.
Okay, so the charge, so just like in this right here, right? The charge is always superscript,
Yes.
always superscript. And these numbers right here tell us how many of each atom. Those are always subscript. So the charge is not at the bottom.
I see. So it's
I-
charge versus
I didn't
number.
cross the charge. That charge just tells us how many of those that I need. Remember, this is just an algorithm.
Right.
How do you do it really? This method right here. That make sense?
Yes.
Thanks for asking. Okay, how are we feeling? Pretty straightforward? So those are for the main group elements.
Is that what it's called, balancing equations, or?
This is not. We're not there yet. Okay? Yep. All this is writing the chemical formula for an ionic compound. Next, let's learn how to name these. Okay? Naming ionic compounds. First of all, before we can do this, we have to know how to name cations. So a cation is just the element name. So what's the magnesium ion called? Magnesium ion. That's it. Mg2 plus is called magnesium ion. What if it's just called Mg, then what is it called? Magnesium, without the word ion. You with me? Okay. So for cation or anions, then we change the ending of the element name. Change. Whoa. To IDE. So we have sulfur here. So what's the sulfur ion called? Sulfide. Okay. And what's the nitrogen ion called? Nitride. Not nitrogide, because it's goofy. Too many syllables, right? Nitride. Good? Okay, so to name these, step 1 is to name the cation first. Step 2 is to name the anion second. Done. So what's the name of this compound right here? Lead sulfide. What about this compound right here? Magnesium nitride. We're going to get to nitrate later. But this is just a main group element, so we change the ending to IDE, not to ATE or ITE, but IDE. Are we good? And what's this called? Sodium chloride. Pretty straightforward. Now, when we get to covalent compounds, we do the same thing. We just add something. The first element is element name. Second element is change the ending to IDE. Done. We do the exact same thing. We just add prefixes. We'll get there. Okay? So you can tell me what this is called. Aluminum oxide. Well, that's not too bad, right? Pretty straightforward. What about this? Magnesium chloride. Okay. Is this written correctly? That might be a good test question. Which of the following compounds are written incorrectly? Are these both written correctly?
That one's
Well, let's see. Aluminum is what? What's the charge? Look at the periodic table. What would aluminum's charge be? Everybody do this. Make sure you can do this. 3 plus, right? And we write that one first because it's the cation, it's the metal. And oxygen is O, 2 minus. We cross these numbers down. Is that what we get? Simplified? Yeah. Is this one correct? Yeah. We got a 2 plus and a 1 minus. Cross them down, MgCl2. Every single time. There's no other way to write magnesium chloride. That's cool about ionic compounds. There's no other way to write it. What about that? That's for covalent, so we're going to talk about it later. But for ionic compounds, there's only one way to write it. Okay? Any questions on naming? So that's just for compounds with main group elements in it. Okay? So let's talk about what if it has a transition metal in it? A little bit different. So let's get this. So naming ionic compounds with transition metals. Okay, so to name this, we will have to be given the formula, is that right? We have to be given the formula. Because we can have FeO, we can have Fe2O3, we could have FeO, hold on a sec. Fe2O. These are all forms of iron oxides. We're going to call them, all three of them, iron oxide? Wait, you just said. There's only one way to write it for main group element ionic compounds. Okay, just main group. So these, we have to name them differently. And we name them because by their charge, because they all have different charges. Now, remember, we looked at valence electrons on the main group elements, right? We can't do that for transition metals. They just are different. Why? I don't know, they just are. Okay? So here's what we got to do. First step, I'm going to leave some room so I can do those in just a minute. Step one is to determine the charge of the cation. In fact, do we need to practice some of those others real quick, or how we feeling? Doing okay? All right. So determine the charge of the cation. Then we do the exact same thing. We write the formula of the cation, formula of the anion, and swap charges. No, that's naming, sorry. No, we don't do that. Sorry. We do that if we're writing the chemical formula. My bad. So determine the charge of the cation. Once we know the charge, we write the cation first. And so that's just the element name, right? So in this case, iron. So that's element, whatever element we're dealing with. And then we put parentheses with the Roman numeral charge. Roman numerals. Do you guys know Roman numerals? Should we give a brief reminder of this? Yeah, let's do it. So we have number 1 is I, 2 is II, 3 is 3 I's, 4 is 1 before 5 because 5 is V, 6 is VI 1 after 5, 7 is 2 after 5, 8 is 3 after 5, 9 is 1 before 10, and 10 is X. That's all we need to know. In fact, we probably won't ever use 10 or 9. But that's what they are. Good? So the Roman numeral represents the charge of our cation, of our transition metal. Good? And then we name this anion second. Using IDE as the suffix, right? Elamide. Same thing, if it's a main group element, okay? We'll talk about it if it's not. Are we okay with that? All right, now let me show you how I figure out what the charge is. There's more than one way to do it. I put a line in between the cation and the anion, and put a line under it just to organize it. And you don't have to literally write this down. I'm just showing you how I'm thinking about this, okay? We have to know the charge of the anion. What's the charge of the oxygen anion?
2 minus.
Yeah, do we all know how to look at that, find that on the periodic table? Okay. And how many oxygen atoms are there in this compound?
One.
Only one. So it has a total charge of all the anions is -2. And we know that all ionic compounds must be neutral, right? That means all of the cations added together must have a charge of +2. You with me? And since there's only one iron, that means it takes the whole charge of 2+. Okay, we figured out the charge of this iron is 2+. So what's the name? Iron, Roman numeral 2, because the charge is 2. You with me? And then name the anion second. This is just a main group element, so it's oxide. Iron, and we read it as iron 2 oxide. Do we have to memorize what charges these transition metals are? No. You'll be either given the formula or the name. And it's in the name. The charge is right there. And the formula, we can figure this out. You with me? Should I show you a different way to find the charge? Okay, so that's one way. I like that way because it always works every time and you don't have to do anything else. But here's another way. We do the opposite of crossing the charges down. We cross them back up. That 3 goes here, and the first one's always positive, right? And the second one's always negative. Is this good? Now that way looks easier, doesn't it? But sometimes you have to simplify to get your formula, right? And if you simplify, those aren't going to be the right numbers. Okay, do you see why I do it this way? Now I'll show you and I'll do it again. Okay, what's the charge of iron in this compound? How do we know that's right? Because oxygen is 2-. If oxygen's charge is correct, so is the transition metal's charge. Good? So this is called iron, Roman numeral 3, oxide. Any questions on that? Yeah, Katrina.
How did you, besides just knowing that oxygen is 2-,
You look at the
how did
period.
you know to add the minus?
Oh, because in an ionic compound, the cation is always first, which is a positive.
Okay.
Anion's always second. Metal is the cation, non-metal is the anion. Yeah.
I have a potentially dumb question.
So hold on. Liana?
Yes,
Okay, what's your question?
hold on. How do you know that that is an ionic compound to begin with?
Great. How do you know it's an ionic compound, guys?
If you have metal as non-metal?
Metal and non-metal. Iron.
No metal and non-metals that are not ionic.
There's no metal. If it has a metal in it, it is always an ionic compound, period of end of story, no exceptions. Yep. Yeah.
In our first problem, we have the charge of iron is 2+, right? Why is it 3+ now in the second one?
That's a great question. Maybe conditions, maybe temperature, maybe, yeah. Great question.
Is it just a different isotope?
Different what?
Is it a different isotope?
I don't think so. That is a really good question. I'm sorry I can't answer that fully. Yeah, Gavin.
Maybe I'm just misunderstanding. How do we figure out the valency of transition metals?
Just like this.
This is the only way how?
Ooh, I'm never going to ask you how many valence electrons a transition metal has.
Okay.
Never. Nope.
Is there supposed to be some way though?
Why do we need to know how many valence electrons are in an atom? So we can figure out its charge, so we can name it correctly. That's it. Because that's the part that changes in a chemical reaction. Does that answer your question?
Well, yeah, that makes sense. I was asking that question because you said the second method, we wouldn't know necessarily if there was simplification. So I didn't know if there was some way I could figure out what the supposed initial valency was.
How do we know this is correct?
Well, because oxygen
Is 2 minus.
2 minus, but I guess I'm saying theoretically if it was different.
We'll get there. We'll get there. Okay? Michael.
Are there ever ionic compounds composed of two metals?
We don't call them ionic compounds. We call them alloys. And they're not chemically bonded. They're just melted together. Yep. Yeah.
You mentioned imperfect simplification, because it might screw up the way you write it. I was wondering if we could give an example.
Yes. That's the next one.
Oh, sweet.
Are we good so far? All right, let's do this one. Now, if I take this 2, so this is a 1. If there's not a number there, it's 1, right? So if I take this 2 and bring it up here, that's a 2 minus, right? Oh, this isn't a good example, is it? Yeah, this is not a good example. Because that's correct. Because this is correct, yeah? Well, we will get to another example. So what's this one called? Iron 1 oxide. Let's do this one. We know it's iron 2 oxide, but let's write it. This is a 1, this is a 1. We cross those 1s up here. This is a 1 minus, this is a 1 plus. Is this iron 1? No, because this is not oxygen 1 minus. So what do? Multiply everything by 2. So the oxygen is correct. If oxygen is correct, so is iron. That's how we would do that. You don't like that, I'm seeing.
Can you go through that one more time?
Yeah, I don't like it either. Because then you have to remember to do that, because sometimes you have to and sometimes you don't. If you do it this way, it's one and done. I'm not saying you have to do it that way because I like to, but I'm just saying that's why I do. Yeah.
So you multiply everything by a number to make your anion
The correct. Yep.
and another one follows.
Yep.
Okay.
Because the ratio is a 1-to-1 ratio. So if we have Fe2 plus O2 minus, then we cross them down, it's Fe2O2. But now it's a 2-to-2 ratio. We have to simplify it, right? To be FeO. You following?
Yes.
So, your choice, it really is. And as you get so good at this, because you guys are going to get so good, right?
Oh yeah.
I would if I were you. You get so good at this, you can do it either way and it doesn't matter. Because you just know how. You know what they are and you just do this in your head and you just do it. But guys, for now, I would find a way, a technique, and then just stick with that technique. Until you get good at it. Yeah.
So the issue or red flag that we should be aware of is oxygen's valence electrons are incorrect.
Yes. Or its charge is incorrect based off of the oxygen's valence electrons. Yes.
Okay.
Because oxygen must be O2 minus, not O1 minus. Good? Yeah.
How do you do it the first way? You just roll it.
Yeah. Well, should we, let's do this one right here? Or should we just do a whole new one? Whole new one? Okay, let's do CUS. Okay? So if we cross I just do this to kind of, and again, you don't have to literally write this. This is just the way I think about it. What's the charge of sulfur ion? 2 minus. And how many sulfurs are there? 1. So that means, maybe I should, that one's basically the same as the other one. Let's do a different one. Okay.
Do the FE, the one on the right side, the way that you like to do it?
What's that?
The iron 1 oxide,
Should we do that one?
can you show that one in the way that you do it?
Yes.
Thank you.
Fe2O. Okay. So what is the charge of the anion? 2 minus. And how many are there?
1.
Y'all see there's just 1? Because there's no number right there, right? So negative 2 times 1 is negative 2. And since all ionic compounds must be neutral, the cations have to add 2, positive 2. You with me? But this time there's 2 of them. But they're both the same. They're both irons. That means you have to split the positive 2 into 2 equal pieces, which is 1 plus. Iron, 1 oxide. Does that make sense?
Yes, thank you.
And that way works every time, and there's just one path. And you don't have to say, okay, do I have to check something else? It's just it. That's it. Let's do another one.
I had a question, Professor.
Yeah.
So you're saying you divided it by the small number, like by the FE?
Uh-huh.
So you divided by 2, so on the other, on the first thing you did, you just divided the 2 by 1, and that's why you saw.
No. Nope. Here, watch this. So here we go negative 2 times 1 of them, because each ion has a charge of negative 2. You with me? And so we multiply negative 2 times 1 because there's only 1 of them. And we get negative 2.
Right.
And we get positive 2 because this has to be the same value, just opposite charge, right? And then now we're going the other way. That's why we divide.
Okay.
We take the total charge and divide by how many there are.
Right.
Is that what your question was?
Yeah, sorry, I was talking about the iron 2 oxide, not the iron 1 oxide.
Okay, same thing. Negative 2 times a 1 is negative 2. This side has to be positive 2. Positive 2 divided by 1, because there's only 1 of them there, is 2 plus, positive 2.
Okay, that makes sense.
Just do the exact same thing.
Can we write that out, like in a step-by-step method?
Yeah.
Yeah, let's do it.
We're beating a dead horse, but if you could slow it down just a little bit and write it out in steps.
Uh-huh. Okay. So step 1. I never written these steps out, so let's see if we could do it. Okay. So determine charge of known ion. Can I do this if I know the charge of the metal but not the non-metal? Yeah, I could just do it the other way around, right? So I'm just going to say determine the charge of the known ion, whatever one we know. Step 2 is divide this charge by the number of atoms of that ion. Are we good there so far? And that'll give us, so if we do this, what's the charge of our known ion? 2 minus. Then we're going to multiply. Uh-oh. I said it wrong, didn't I? My bad. Multiply. Sorry about that. This charge by the number of atoms of that ion. So we multiply the -2 times the 2, and we get -4. And then step 4 would be multiply that by -1. Multiply this number by -1. And -1 times 4 is +4, right? There might be better words to, I'm just making these steps up as anyway, but
Is it always -1? You always
yes,
multiply
because
that
it's
by-
always the opposite. And if you multiply by negative, if it's the positive, you multiply -1, it's negative. If it's negative, you multiply -1, it's positive. These are always going to be the opposites, yeah.
Is the transitional metal always gonna be the unknown ion?
No. Maybe you have an unknown ion, but you're using a main group cation, and you know the main group cation, right? So you could do this either way.
But I'm saying if you have a compound with an anion and a transitional metal, the
Yeah.
anion is always known.
Yes.
Okay.
Yep. Well, we should know it.
Yeah, yeah.
We're going to be talking about polyatomic ions, and if you don't memorize them all, you won't know it. I'm just saying. Okay. And then step 4 is divide this number. It's not very beautiful, guys. By number of atoms of unknown element. So we're going to take this number and divide it by 1, because that's how many atoms we have of the unknown element. So I'm going to get a 4 plus. So what's this called? Lead, Roman numeral 4, sulfide. Hold on a sec. Is lead a transition metal? Neither is tin, but tin and lead follow the patterns of the transition metals. Why is that? Is it going to gain 4 electrons or lose 4 electrons? Not either. It's like a transition metal. It's a variable cation, like the transition metals. Why? I don't know, it just is. Yeah.
Does the whole group behave that way, or is it just like those two?
Those two. Why? Those are the only 2 metals in that group. The rest of them are either metalloids or nonmetals.
So will the metalloids and nonmetals go either way?
Most of them will be a covalent compound, so it won't gain or lose anything. Good? So yeah, that's all you need to know about that. Did that help, Trina?
Yes, thank you.
Good. Thanks for asking. Sorry it's a little clunky, but I didn't refine it. But okay. Now, are we good with naming ionic compounds with transition metals in it? Should we practice some more? You guys got a whole worksheet right here. You want to try some today? Okay. So we are dealing with section 4. And I have practice examples for all of these that we've done so far. So, and the answer key and this is on Canvas on the home page. You can always go to get it from there to make sure you're doing it right. All right? All right, let's see. Let's do, you want to do the first one?
Yeah.
FeCl2. What way do you guys like to do? You guys like drawing the lines or you like to cross them up? Okay. Always works every time. You don't have to do anything different. That's why I like it. Okay? So where do we start? Chlorine's charge is -1 or 1 minus. Good. And you guys, I don't care if you write it -1, guys. I really don't. Then what do we do with it? Multiply by 2 is -2. That means the charge of the cations must be +2, and there's only 1, so it takes all of it. This is called, we use the element name for the cation, just like always, Roman numeral 2, because that's the charge. What do we do with chlorine? Change the NE to IDE, because it's a main group element. We're good? Is there another one on there that's like, I want to try that one because that one looks icky? Yeah.
Right underneath the first example, it goes Cu2O.
It should be. Because I had to subscript all these and I missed that one. Typo. Yeah, that's Cu subscript 2O. Maybe while we're here, I'll give you the exceptions. I don't know that they're on the test, but there's a lot of things that's in this course that normally I don't teach. So, like when I say normally, I mean in my high school class. Okay? So let me give you the exceptions to the so I gave you 2 exceptions. Tin and lead follow the transition metals. And I'm going to pull up a periodic table because it's easier to use it to give you these exceptions. All right, we got zinc, cadmium, and silver. These are they only have one cation. They're not variable. And here's how I remember what they are. Silver is in group 1, 1. So it is 1 minus. Silver, not minus, guys. 1 plus. Why is it plus and not minus? Because it's a metal. Metals are cations, remember? I did that on purpose so you guys would just never, sorry. Hope I didn't confuse you. All right. And what about zinc and cadmium? What's their charge going to be? 2 plus. Good? So if I have AgCl, what's that called? Silver chloride. We don't even have to write silver 1 chloride. It may or may not have a 1, I'm just saying. If it has both on there, I'm on your side. Okay? I'm just saying. Because that's a tricky question.
And just a question, the test or the exam is gonna be always, is the only multiple choices?
Yes.
You don't expect
And that's what, I didn't write all the multiple choice, I didn't write this. So if they say, okay, here's my options. This is silver chloride or silver 1 chloride. If that ever happens, and you choose one of them and it's wrong, I'm going to give it to you. You have to let me know. Yeah.
Could you figure this out just by doing what we have been doing this entire time?
You could. Right? We could do this. This is 1 minus, this is 1 plus, right? Has to be because it's a 1-to-1 ratio. But then how do we name it? Right? That's the only difference. So if you call it silver 1 chloride, I'm not going to dock you. I will not. Okay? Because It could be called that, yeah.
You're just saying, these will always be either silver or silver one, and then like zinc two, and then cadmium two.
That's right, always.
Always.
Like the other ones, we did iron, that had 3 different charges,
Right.
right? These 3 do not have 3 different charges.
Is that just based on
Let's
their
have-
ability to bind, like to become ions, to compound? Like, it's just the way they can?
Why is it that way? Great question. We just know that it is. Yeah.
Can you explain one more time why you dropped the one when writing the name? For silver specifically?
Because it's always silver one. Why did we write iron 2 chloride? Because sometimes it could be iron 1 chloride maybe, right?
Because
It has 2 different options.
I see.
That's why we write it with the Roman numeral.
Because it depends on what the anion is?
Not necessarily, but the charge, right? So, since there's only one way to have silver and chlorine, then we just call it silver chloride.
Oh.
But again, I'm not gonna put up a fit about that. If you put silver 1 chloride, great. Okay? All right. Are we good with writing chemical formulas, naming ionic compounds with transition metals? Okay, let's write chemical formulas now. This should be pretty straightforward if you understand everything we've done today so far. So if we have nitride, if we have 10,8 nitride, can you write the chemical formula for this? It's the same way I showed you how to write the chemical formula for ionic compounds. They're all the same. So what's the first step? We write the ion formula of the cation first, which is SN8+. You with me? This Roman numeral tells us what the charge is. And nitride is N. What is it? Look at the periodic table. 3 minus. Do we get that? Now what do? Cross these numbers down. And we get SN3N8. It's a ratio of 3 to 8. Can we simplify that? Nope, that's good. Not too bad, right? Okay. Do we need to do another example? Yeah? Okay. Let's do lead 4. Uh-oh. Selenide. Okay, lead 4 is, tell me the ion formula. PB what? 4 plus, right? And selenide is Se2 minus. Good. Now what do? Cross the numbers down, and we get Pb2Se4. Are we happy with this answer?
No.
What do we got to do?
Divide.
Simplify. Divide both of them by 2, and we get PbSe2. Questions? Is that halfway?
Yeah.
Did my thing go off?
Yeah.
Okay. Sometimes I'm just so I missed. Okay, let's take a break. Let's do some little tricky problems. I mean, seems like, never mind, we'll just do it. All right. So let's see here. So let's say we have a compound let's change the color. SRX, and we don't know what X is, but we know X, let's see. We want to know X must be from which group? So let's find out. X is an anion. How do we know?
It's not a metal.
But how do we know?
Don't they always have to be a combination of metals and non-metals?
It's the second atom in the element, in the compound. Yeah. It's cation and anion. How do we know strontium is cation? Because we know where the metals are on the periodic table, yeah? Are we good? Okay, thank you. All right, so we got to figure out what group X is from. In order to know what group X is from, we would have to know its what? Charge. Okay. So can we figure out its charge? Yeah, we know how to do this. But this time we have to figure out the charge of the anion. So we have to start with the charge of the cation. What's the charge of strontium? 2 plus because it's in group 2. You with me? Has 2 valence electrons. It's going to lose 2 electrons and become 2 plus. You following me? Yes or no? Okay. There's only one of them, so it has a positive 2 charge. That means the anions have to have a total charge of negative 2, and there's only one, so it's a 2 minus charge. So what group is it from? 16. Easy enough? Okay. Let's do another one. That may be not as easy. Let's say we have XS2, and we know the X ion has 78 electrons. What is X? What can we do right now? Figure out its... Oh, hold on, is this an ionic compound?
We don't know yet.
We do know. What tells us it is or it is not? It's made of ions. Therefore, it is an ionic compound. That means X must be a metal. Are we good? So we're going to do the same thing here. What we just did. This is 2 minus charge because it's sulfur. You with me? There's 2 of them. That's not an 8, that's a 2. There's 2 of them. That means it has a total charge of negative 4. That means this side must be positive 4. There's only one, so it's a 4 plus ion. That means, hold on a sec. X, that's not an ion, that means just the elemental X, or actually let's say X4 plus has how many electrons? 78, because it tells us, right? What had to happen for it to become 4 plus? It lost 4 electrons. So how many electrons does X have? Try again. It lost 4 to become this, right? That means it has to have 82 electrons before it becomes an ion. Do you see how that's a little tricky? But if you really think about it, maybe not so bad. I don't know. Tell me. Okay? If the element, the neutral element, has 82 electrons. How many protons does it have? Also 82. That means this element is lead. Do you get that? Should we do one more?
Are we like finding an unknown?
Yeah, we're looking for X.
Oh, okay.
Yep.
I had no idea what we were doing.
Okay.
We go a little slower.
Yeah. All right, so let's do, I don't have another one of these, so I'm going to use the periodic table to figure this out. Maybe. Okay, let's do. And the X ion has 23 electrons. What is X? Do you want to try it or do you want to do it again together?
Try it.
Okay.
Can we do it together?
We will, 100%. So use what we just learned today to help us to figure this out. What do we do first?
Find the valency of.
Find the charge of the X, right? What's the charge of oxygen?